Hey there, welcome back to VCV Essentials, and if you didn't watch my introduction video, please go ahead and do so just to get a few thoughts on all of this. So, I'd like to start with review from our previous classes just to give you like an extra set of notes but on video, so you can always come back and re-watch these. I said that there are 4 types of signals that we're going to be playing with in our modular synthesis study: audio signals, gates and triggers, clock signals, and CV signals. I emphasized that all 4 of these are just some version of voltage getting stronger and voltage getting weaker. When it came to audio signals, that's what we hear. That is what we are listening to. So our audio signals will most likely start from 2 possible sources for us right now. And the first of those is the VCO, voltage controlled oscillator. If the sound we are ending up with contains a pitch element to it, if we can play it with musical notes, it's probably going to begin with some type of a voltage control oscillator like this one. The other possibility was a noise module. Noise just sounds like static on the radio. You can think of it like that, although you'll notice in this particular noise module, the noise comes in several flavors. We heard those in class. You can always experiment with them on your own. And our audio signals will be starting from one of these 2 elements. All of our audio will eventually come out of the module called audio. We've been using this one in class. I need to set this so that you can hear it. Let's see, what am I using? I am using Pro Tools 2A is what I'm using. And so I'm going to turn this down. I'm going to turn this down just a little bit so it's not jarring when I first hit that. If I connect the audio output to the noise module, you can hear it, and you can hear it has a pitch component. Indeed. If I connect noise to the audio module, you can hear it, and you can hear it doesn't really have a pitch component. Just different types of that staticky radio noise. I gave you a couple suggestions, and one of them was when we create patches, it's kind of helpful to start with the sound source, the actual audio module, whatever it is, VCO or noise, on the left, and then work our way to the right so that we can always trace how the signal is moving. Left to right tends to work for us here in America. And I also asked that if you're turning this into me, you right-click and choose a cable color, and I like red for audio. So red is my audio signal. Cool. Those were the audio modules. Let's talk about the next possibility, gates and triggers. Now, we don't listen to gates and triggers. They are not audio signals. We use gates and triggers to control when events occur. Now, in order to understand this, let's use a scope. Zoom out a little bit here. The scope lets us visualize what the electricity is doing. And I'm going to begin, there are a few options that I list here. I am going to begin with a push module from VCV Rack. Because push basically is a 1-button gate or trigger output. Remember, the outputs are highlighted in white. Let me send trigger to input number 1 as a blue trace. And let me send gate to input number 2 as a green trace, and I'll separate these a little bit so we can keep our eye on both. You can see the green on bottom and the blue on top. When I press this button, it will send an output from both trigger and gate. And the difference we should be able to see is, let me take time out just a little here. The difference we should be able to see is that trigger will be an instantaneous burst of voltage, just a very quick spike. Whereas gate, it will matter how long my finger or my mouse click here stays on that button. So both of these are just quick voltage up, voltage down. But gate allows for duration, for sustain. So the longer my finger stays on the button, the longer it stays up. Let's watch this. Here's a quick push. You can see the green trace was a little longer. Here's a longer push. There you can see the green trace was much longer. And we use gates and triggers as a means to say, now. Whatever the event is, trigger it now. Very often, gates and triggers are connected to an envelope of some kind so that we can do something to shape that voltage so it's not just all the way on or all the way off. Gates and triggers, just all the way on, all the way off. Sometimes we will use an envelope so that we can slope up or slope down, and we'll talk about that more. Other options in VCV for gates and triggers, we've got this module called Pulses, and the Pulse module has both a trigger and a gate output as well. It's basically just the push module, except it gives you 8 different triggers. So you can have these each going to a separate event. You can basically think of this as like you could create a soundboard where just every time you hit the top one, you know it's going to make a noise that sounds like an air horn, and every time you hit the second one, you know it's going to make a noise that sounds like thunder, and so on and so forth. That's our second possibility. Oh my God, if you want a little behind the scenes here. So I was just editing videos that I recorded last night, and here, let me pull this will look weird, but let me pull my video recording software over to this screen. If you're looking at my microphone level here, there is a hotkey on OBS that mutes my microphone. It is M, so I'm talking, I hit M and it mutes. All right, but I'm looking the VCV screen. So it turns out that at some point, while I was talking about gates and triggers, I went to type the word MIDI into VCV. So as soon as I hit M, my microphone muted. I never noticed it. I talked for another 15 minutes or so. So I have changed back into the jacket and shirt that I was wearing. I'm going to recreate most of what I was saying at this point. I had just finished talking about the push and pulse modules and the difference between triggers and gates. But the way we have been getting gates in class so far is by using our MIDI controlling keyboard. So when we press a key down on the keyboard, the gate opens, stays open until we let go of the key, then the gate closes. So in order to access a gate that way, MIDI to CV is the module we need, because what gets spit out of our keyboard is a MIDI code, and what modular synthesizers look for is a control voltage. So I'm going to assign the keyboard I'm using. In this case, it's an Arturia KeyStep 32. And there you can see the most common types of outputs that we would use from a MIDI keyboard are all listed here. It's the gate that I'm concerned with right now. Send that into the scope, and now you can see when I press a key on my KeyStep, the gate opens, and it stays open until I let go of that key. Cool. Let's talk about clock signals. Clock signals are a kind of gate or trigger. They're just a gate or trigger that repeats at a steady interval. So the steady interval is, musically, we think of that as tempo, and we measure it in how many of those beats or how many of those open gates happen per minute. We say beats per minute. That's musical tempo. But frequency, remember, so you'll notice this right now is repeating at 2 hertz, meaning 2 cycles per second. 2 cycles per second would be 60 times 2, so 60 seconds in a minute. That's 120 beats per minute. If I just take the square wave out of here, we can see, let me slow this down a bit. We can see that going up and down 120 times a minute. If I do this, we can really get a good view of that. So musically, that tempo would be 120 BPM. That's a gate, you notice. It has what we would call a 50% duty cycle, which means that it's positive, it's open, and it's negative, it's closed, or it's 0, are equal. So it's 50% open, 50% closed. So the way we could turn that into a trigger is by making the open signal as minimum as possible. I can do that with pulse width. Now it's really a trigger. It is just an instantaneous spike happening 120 times every minute. Let's initialize that. Or 2 times every second, right? There are dedicated clock modules that are not just LFOs, but LFOs work plenty well. And VCV doesn't come with, well, VCV has a clock built into its sequencer, which we'll look at in a future video, but otherwise does not have a dedicated, just a clock module. They expect you to use probably an LFO to do that. CV signals. Now, here we get into it. The main types of CV signals that we are using in class are going to be envelopes and LFOs. So I kind of have already demonstrated some of this. Let me move this stuff a little further away. Let's get an audio module. Again, I think the way I demonstrated this in class was with a VCO and an amplifier, a VCA. As my audio path signals. See if we got that. Oh yeah. Oh yeah. And then I was using either an LFO or an envelope as my CV signal. Let's use the LFO right now. So I could create this effect using the LFO to control the volume of the amplifier. We would call this tremolo if I wanted to go faster, if I wanted to go slower. Right now I'm using the sine wave. If I used the square wave, it would just be an off-on. Which you can see does not sound nearly as smooth to us. Sine wave sounds smoother. Or I could use that LFO to control the frequency of the VCO. Turn that down. I have this LFO, this sine wave, at a very slow rate going to the frequency input, meaning it's going to be the same as if I grabbed this frequency knob and moved it back and forth, or, you know, up from where it defaults and then back down to its default position. So right now you'll notice, though, we're not hearing any frequency change. And that is because of this knob right here. This knob right here is called an attenuverter. If I zoom way in on it, we can see that it shows us a percentage of change, and it is set to 0% right now. So whatever is coming in here, it is having 0% of an impact. It's nice to have an attenuverter. If we didn't, then as soon as I connected this cable, if it was affecting pitch by 100%, it sounds like this. Let's turn it back up here. And although that might be interesting, it's not what we want, not hardly. I just want a little pitch waver, just a little like vibrato, like a voice would have. So I want way less than 100%, and the attenuverter lets me do that. The attenuverter lets me say, it's even going to be less than 1% for me. It's going to be like 0 point something. That's 0.7. Now the speed's a little slow. It doesn't quite sound like vibrato on a voice, but let's take it up. There you go. That kind of has a vibrato sound to it. Just barely opening that. And right now, because of the way the LFO works, turn this back down. Right now, it is basically taking this knob and going up by just almost 1% and then back to its default position here. We can see on the scope, if I grab a copy of that cable that it never gets lower than 0. So 0 in this case is like default, where the knob began. So it only goes up to the positive. However, if I changed this, there's a little button on LFOs that says offset. Right now we would call that a unipolar signal. If I made this a bipolar signal by changing that offset, you'll see on the scope, it now centers around 0 and goes a little up and then a little below. So that would be the same thing as moving the frequency knob a little above default and then a little below default. Should sound pretty similar. Let's hear it. Sounds nice. So that is using an LFO as a control voltage. I was controlling either amplitude or frequency, but we can control, remember, we can control just about anything that we can touch with our mouse. Some module will give us the ability to use a CV for that. So the other possibility, if we're not using an LFO, or maybe in combination with an LFO sometimes, is an envelope. In my VCV modules, it's just ADSR. We are going to look at different types of envelopes later, but ADSR is by far the most common. If I use this to control amplitude, then my gate signal can do something beyond just loudest to nothing. It can be shaped, so it can get loud at a slower rate and then get quiet again at a slower rate. I would connect the envelope output to the VCA. And then I could either use this push button to open the envelope, which is going to, I can set to have a slower rate, like I said, or we can use the MIDI to CV module that we've got here. Set my keyboard again, send my gate signal to the envelope, and then the keyboard will just trigger the envelope or gate the envelope, and the envelope will determine how fast or slow we get loud. Let's make it nice and slow, and let's just hear this. Let's even make that attack slower. Now it's sustaining, meaning as long as my finger stays on there, it keeps making noise at that volume, because this is a gate signal coming out, not a trigger. And when I let go, it gets quiet at that rate. Very good. Makes sense, and we're happy with that. And I have not muted myself again. Congratulations, me. However, we could also use CV to control so many other things, and like I said, the most common CV outs from a keyboard are listed here on this MIDI to CV module. Volts per octave is a pretty important one. Take the volts per octave output of my keyboard to the volts per octave input of VCO, and it will scale the notes of the keyboard to adjust the frequency knob. So the VCO module defaults to C4. But now if I hit the D key, it will actually scale the frequency to be the pitch D and E and F and so on. So that gives us the ability to have pitch. And we will find out using CV is what makes this whole process amazing, because we tend to modulate just everything we can, because synthesizers can sound very robotic and dull, but boy, adding movement to parameters just brings life into the whole thing, and is something that we're going to love doing later in our projects here. Okay, that is probably enough for this video. Thanks for your time and attention, and I will see you next time.